We noted before that the study of differential equations would be similar to the study of integrals because with both we had information about the derivative and wanted to know about the original function. Similar to integration again, we will learn techniques to solve differential equations. That is, in different situations, we'll solve differential equations in different ways. So, recognizing different types of differential equations will be helpful in recognizing which technique to use. So in this lecture, we'll learn some adjectives that describe different types of differential equations, many of which we'll learn to solve throughout the course. All differential equations we've focused on so far and that we will cover in the course are ordinary differential equations. An ordinary differential equation is a differential equation which uses ordinary derivatives. In contrast, a partial differential equation is a differential equation which uses partial derivatives. One of the classic partial differential equations is the heat equation, given by alpha squared times the second partial derivative of u with respect to x is equal to the partial derivative of u with respect to t, where alpha is a constant and u is the heat on a wire at position x and time t. In future courses, you may study partial differential equations, but again in this course, we focus on ordinary differential equations. In some applications, we will have two unknown functions with the same variable t. A classic example of this in ecology are predator-prey models. Recall that we studied field mice and owls in a previous lecture. We may want to revisit our owl and field mice model though to factor in what would happen to the owl population, as it would depend on the amount of field mice. Previously, we just focused on the population of field mice. In a case like this, when we have differential equations for two different functions that depend on a single variable and each other, then we call this a system of differential equations. For example, the system of differential equations dx dt is equal to ax minus alpha times xy, and dy dt is equal to negative cx plus gamma times xy. This is the general form of the predator-prey model, where x is the population of mice and y is the owl population. Then in this model, the owl population benefits from the mouse-owl interaction, the xy term, with a positive constant gamma in its differential equation. Conversely, the mouse population is negatively impacted by these interactions. So there is a negative constant, negative alpha, of the interactions of the differential equation for x. We'll study systems of differential equations later in the course. For a single differential equation, the order of a differential equation gives the highest derivative that arises in the differential equation. For example, what is the order of the differential equation p triple prime plus 2t times p double prime plus e to the 5t p prime plus p to the 5th power equals t to the 7th? Since the highest derivative involved is the third derivative p triple prime, we would say that the differential equation is of order 3. Another characteristic of differential equations that we'll want to keep track of and we'll use different techniques on are linear versus nonlinear differential equations. The first type of differential equation that we will learn to solve is called the linear differential equation. And all the examples we studied so far are examples of linear differential equations. Suppose we have a differential equation of y equals y of t, written as f of t, y, y prime, up to the nth derivative of y is equal to 0. Then we say that the differential equation is linear if the function f is linear in y, y prime, up to the nth derivative of y. Notice here that t is not included on this list. Another way of saying this is that we can rewrite the differential equation as some function of t times the nth derivative of y plus another function of t times the n minus first derivative of y down the line to some function of t times y itself is equal to a function of t g of t. Again, I want to stress that each of these functions of t need not be linear. We just need to make sure that the equation is linear in y and all of its derivatives. And if a differential equation is not linear in y and its derivatives, then it is called nonlinear. And again, there's no condition on each of the functions ai in whether or not they are linear. The differential equation could be nonlinear in t and still considered a linear differential equation so long as it's linear in y and all of its derivatives. The last thing that we'll define here is the solution of a differential equation. We define a solution of a differential equation on an interval from t between a and b as a function y equals some s of t that makes the differential equation true. That is, if we plug in s and all of its derivatives for y, the differential equation f at t s s prime up to the nth derivative of s is equal to 0. And it's relatively easy to check if a function is a solution to a differential equation. For example, we don't know yet how to solve the differential equation y double prime plus y equals 0. But we can check that the function y1 equal to cosine of t is a solution. To check this, we'll want to take the derivative, y1 prime is negative sine of t, and y1 double prime is negative cosine of t. And since the second derivative is negative cosine t, we can see in our differential equation that y double prime plus y is negative cosine t plus cosine t is in fact equal to 0. So y equal cosine t is a solution. You can check on your own that y2 of t equal to sine t is a solution as well. Note that we didn't learn any method here to solve this differential equation, but used it as an example to show that it's easy to check our solutions once we find them.